I think, the more math, the better, is true of everything in life, but that's probably just me. For the most part, I find that understanding the idea behind something is a lot more important than the technical details. A few ways I've found intuition for more abstract mathematics to be helpful. Machine learning. Knowing what could go wrong. Yes, neural networks can approximate a piecewise continuous function arbitrarily closely, but there's a reason that they will often converge to a solution which does poorly around the discontinuities. Rather than spend hours running experiments on this, I can guess it and run a half-hour sanity check. Knowing what did go wrong. Same thing, but hindsight makes things easier, and sometimes harder. To find the right way to think about your model. For example, kernels in SVMs come from transformations between inner product spaces. In classification problems, this allows you to choose an inner product space in which the data is more easily separated and map that separation back to your feature space in an efficient way. Sometimes this is a useful way to think of it. Other times, it's more helpful to see a Gaussian kernel as a weighted nearest neighbors algorithm. To know when ML is the unnecessary. Recently, after learning I was using convolutional neural networks in my research, someone came to me with their research problem and asked me to apply CNNs to it. Instead, I found an analytical solution and proved that, given the information they had, it was impossible to construct a more accurate solution. It took 2 hours to develop the solution, 30 minutes to implement it, and another 3 hours to prove it was optimal. In that time, I could have trained a mediocre CNN that took longer to evaluate the input, had to be retrained for each application, and would never be as accurate. What I'm saying is that I believe ML should be a last resort. If there's obviously no viable analytical solution or you don't have time to search for one, go ahead and skip to the last resort. If your goal is to find the best solution, it's usually better to try an analytical approach first. Understanding math has allowed me to skip some of the hundreds of hours of experimentation normally needed to gain an intuition for ML because I can make educated guesses about what will happen and why and just do quick sanity checks. I still have a very long way to go though. Statistics. Obviously, statistics is vital to data science, and understanding math can help a lot in understanding statistics. Until very recently, I had avoided statistics like the plague. I was only interested in pure math. Just like in ML, math lets you jump right in. You can quickly understand what assumptions matter in practice and which are really only important to the theory. Sometimes your problem won't fit nicely into a paradigm in your textbook. Those times, a solid base in mathematics helps you to develop your own theory. What math is most helpful? Linear algebra. Of course it is. You need it if you are going to do pretty much anything else on this list. If you have a solid understanding of singular value decomposition, you'll be fine. Numerical analysis. Numerical analysis is about determining whether an algorithm will work in practice. Computers don't store numbers exactly, so even when the math checks out, the algorithm can still fail. Let's be honest. No one but NASA analyzes their code that intensely before even running it, so most days numerical analysis won't come up. But one day, you write some code, you run it, and it returns some crazy nonsense values. Numerical analysis tells you exactly where you went wrong. I'm not advocating doing a full analysis of your algorithm every time it goes nuts, because numerical analysis is really tedious and pretty impractical when your job is to explore data quickly. Maybe for some production code though, some practice with numerical analysis is most important for the intuition it gives you so you can guess where the problem is. Number 1 rule of numerical analysis: Taylor series is king. Numerical analysis includes some other tools though. Interpolation methods, polynomial, trigonometric, splines, etc. Fast Fourier transform. Absolutely understand Fourier transforms. They speed up convolution, find patterns in time series and images, and a lot more. Measure theory, particularly the Lebesgue integral. Going in depth isn't necessary. Just understand the basic ideas and it'll really improve your intuition for probability. Optimization. This is a huge one. Different optimization techniques affect rate of convergence as well as amount of memory required. Knowing which to use will be the difference between building a good model and crashing your computer. Trust me, I've done both. But again, I think the greatest benefit is the intuition you get for how an algorithm converges. Statistics. That's only sorta math, but obviously it's a big deal. Know as much of it as you can. Differential geometry. No need to go in depth here. I have to admit though, while starting write an example of some differential geometry concepts you'll never need to know, I thought of an interesting potential application of it to machine learning, so don't be afraid to learn too much. When you specify an ML model type or the structure of your neural network, you're defining a manifold over the space of all possible functions and hypothesizing that the function you want to approximate exists close to that manifold. Once you've fit your model, you've defined another manifold, your function, which you hypothesize that every point in your testing set will also be close to. It's pretty much impossible to visualize these manifolds accurately, but you can still gain a little, intuition again. I found this particularly helpful when designing an algorithm to optimize multiple models at the same time in order to remove the noise from each of them. Those are the main things that come to mind at the moment, but I'll edit this if I think of something else.